There's this huge open environment with counters.
Limited access to a distribution, either through samples or through some kind of noisy queries or something. And so it only gets this kind of skinny pipe. And intuitively, if you start with a learning algorithm, it's easier to kind of take what it does and compress it down into differentially private output. So I think this is just a very high-level intuition for why tools from learning should be useful for designing differentially private algorithms for sort of any task you want to do. And I think, so I'm not a historian of differential privacy, but I think the first time kind of learning and differential privacy were connected was in a work by Ullman, McSherry, and Nissim, where a connection was made to kind of the statistical queries learning model. It was also developed in an influential paper by Kasivaswanasan, Lee, Nissim, Raskolnikova, and Smith on actually designing differentially private learning algorithms. So this has been a very well-explored area. And let me say sort of two reasons why I think it's important to be aware of this kind of connection and the techniques that come out of it. So one is that when you use this sort of techniques, you end up getting sort of powerful algorithms with very clean and qualitatively strong guarantees. I'll say more specifically what that is. But I think this is a point that shouldn't be overlooked, that in privacy, we don't really know what's possible, or especially when these techniques were coming out, we really didn't know what was possible. And getting these very qualitatively clean and strong statements, I think, was very important for clarifying the potential to do things in this area. And also, with respect to the way I'm going to define the problem and these strong guarantees, learning theoretic techniques are going to give us kind of nearly optimal algorithms. So I think, for a reasonably defined problem, when you get nearly optimal algorithms, that means there's something useful going on. So hopefully I'll sort of convey what the techniques are, and that can lead people to use them in various other settings. So let me tell you what problem I do want to solve. So I said I'm not inherently solving a learning problem. I want to solve this problem called private counting query release. So what's a counting query? It's just I take a database. It's got n records, each one with d bits of information about a person. And I want to know what fraction of records satisfies some property q, any property I want. All right, so these, by the way, are two important parameters for the talk. N is the number of people. Each one gets a row of the database. D is the number of bits per row. All right, so here's an example of a query. It's satisfied by these three people, but not the first, so the answer is 3/4. All right, simple enough. And I don't just want one counting query. That's not very much information. What I want to do is I want to produce some kind of rich summary of the database. So I want to design some algorithm that takes a database and some very large family of queries. Or think of it conceptually as very large. It's sort of all the queries you might want to ask. And it's going to output some summary. So I wrote here that it'll output just a list of answers. But really what it's going to output is just some sort of algorithm that lets you answer one of the queries in Q. Maybe a database, for instance, would be a nice thing for it to do. And I'm going to say that it's accurate if any of the queries in this set big Q, I can get an accurate answer from the summary. All right, so the answers to queries in Q range from 0 to 1, so I have some small parameter alpha that says how accurate I want the answers to be. And I want this to hold for every Q. All right, so notice the way I've defined the problem, it's very strong. So there's no reference to a distribution. I want this to work for every database. I don't assume anything about the queries, except maybe I have some bound on the number. And I want to be able to accurately estimate the answer to every query. So this is what I meant when I'm talking about solving kind of a very strong, clean problem. And all right, what I want to do is not just solve it accurately, but I want to solve it in a differentially private way. Katrina gave a very nice tutorial on this, so I'm not going to walk through the definition of differential privacy again. It's not technically so important for the talk. I do want to call attention to the fact that when I say differential privacy, I always mean this kind of two-parameter epsilon delta definition. So you can always kind of adjust what I'm saying for epsilon 0, but for people who kind of know the results, if anything looks unfamiliar, this might be why. All right, this is the problem. And what do I want to do to sort of quantify how well I've solved the problem? The two parameters that I'm interested in are the amount of data required. So this database consists of some, let's say, samples from a population. I want to know how many samples I need to collect. And I want to know as a function of various other parameters, like the accuracy, the number of queries, the number of attributes. And I'm going to focus mostly on this, especially for the first half of the talk, but I also care a lot about the running time of the sanitizer. That's going to turn out to be an important kind of challenging issue for designing these algorithms. Right, is the problem kind of clean enough, clear enough? All right, so here's a very quick history of sort of, the highlights of what you need to know about this problem. So the first thing you try to do is just take all of your queries, write down their answers, and add noise independently to each answer. This is, as Katrina said, kind of the canonical way people think of solving a differential privacy problem. And I claim this is not a great solution because, I want to think about answering a lot of queries, and the amount of data I need to have is going to grow kind of as the square root of the number of queries. So that's not very good. It's not a great approach to solving the problem. Fortunately, is a very exciting result of Blum, Liggett, and Roth from about 5 years ago now, where they showed that you can get an exponentially better dependence on the number of queries. All right, so the amount of data I need only grows logarithmically with the number of queries. It has a somewhat worse dependence on the other parameters, but the point is I can now, given a database of size n, I can actually answer exponentially many queries on the database. And this was sort of the first paper that kind of, I think, explicitly connected learning theory to this problem. And there was a long line of work giving sort of various important improvements. I don't want to ignore them, but I just want to abridge the history a bit and jump forward to what we have now, which is the private multiplicative weights algorithm. So this is a very kind of nice algorithm for solving this problem. It gives good quantitative guarantees. It gives good qualitative guarantees. It was introduced in a paper by Hart and Rothblum, and various kind of variants on the algorithm have appeared. And some of those variants I'm going to talk about involve some work that I was a part of where we sort of put this multiplicative weights algorithm in kind of a general framework that makes a very kind of modular connection to learning algorithms, and also leads to kind of tighter analysis of the algorithm. And also in subsequent work, having this general framework has led to sort of several improvements for special cases. And I think this is kind of where a lot of the, sort of the action is in these problems. All right, so this is actually a pretty good kind of summary of what the talk is going to be about, is basically this slide. Now, of course, saying that, I have another summary of what the talk is going to be about. So the first thing I'm going to do is I'm going to introduce kind of just a generic blueprint for how you might solve private counting query release. And it's a blueprint that we sort of formalized in a paper with Anupam Gupta and Aaron Roth. And, so let me tell you, let me just sort of say how I think is like an intuitive way to solve these problems. So on the right, you have the raw data. It's, you can't, this is private, this has to be private output. The data sits behind it. And we have to think about what we can get through this barrier. So maybe a reasonable thing to do is, without even looking at the database, we'll start with some very crude guess of what the database might be. Presumably we will fail, because why would we be able to do this? And we'll now kind of send through the privacy barrier a question. We'll ask, is our approximation good for answering all the queries in Q, all the queries we care about? And it probably won't be, so we're going to need something about the real database. We're going to need some kind of hint. Can anyone think of what might be a good sort of hint that we'd want to get about the database? Success. All right. Fantastic. So, I mean, if it's not good for Q, there must be some query it's not good for. So I'm going to try to get the sanitizer to tell me some query that I don't answer well. And then, given this information, I want to have some clever way of improving my approximation to the database. So I have some algorithm U that takes the query in the database, so it takes this as input, and it's going to come up with a slightly better guess of what the database is, hopefully. All right, and not surprisingly, we're going to repeat, because we're probably still not there. And hopefully we get another query, and we continue to refine our guess until, after we do this for capital T steps, we're done. We have to actually find out that we've managed to come up with a good approximation, at least with respect to all the queries in Q. And this is sort of what the output will be. Once we have this, we might as well just give it out to the world. Right, for people who sort of like pseudocode better than funny pictures, basically, the algorithm takes the database, it starts with some guess, and then it runs this loop where in every round it finds kind of the worst query. Might as well find the worst. And does an update with it. All right, so what progress have we made? So far, I haven't done anything for privacy. But the progress we've made is that we sort of decomposed the problem into smaller problems. Fortunately, differential privacy composes well, so if we can solve each of the small problems with differential privacy, we can solve the big problem. And we've also done something else, which I think you'll see later is kind of nice, which is that we sort of separated privacy. So the only part where we touched the data was finding these queries to do updates with, and we separated that out from how we do the updates. So from a privacy perspective, we don't care how we do the updates. All right, so you can plug in any update algorithm for free, at least in as much as you can make this framework. OK, but I haven't really told you anything yet that makes this like a non-trivial approach to solving the problem. Maybe this process works, but it doesn't finish until you've asked all the queries. All right, so you get the answer to all the queries. You haven't really solved anything. So we need one more thing to hope for, is that we've hopefully decomposed the problem into a smaller number of subproblems than there are queries. And maybe a priori there's no obvious reason why you should be able to do this. Maybe each query just conveys new information. But it turns out that using kind of the theory of online learning, in particular no-regret algorithms and the multiplicative weights update rule, it turns out that we're actually going to be able to use a small number of queries in order to approximate the database well. So I'm kind of guessing that many people have seen kind of no-regret learning and multiplicative weights. But let me go through it. And if I go through it too fast, feel free to slow me up. So the model, so let's back up from private query release for a second. The model is I have some set of experts. Maybe these are financial advisors. And I want to distribute my dollar of investment every day between the financial advisors, and I want to make sure that I don't pick the worst ones. So every day I split my dollar into some distribution over the experts. I give 25 cents to each expert to invest, and then I find out how much money they lost. All right, so you can tell how much I think of financial advisors. They're always going to lose an amount of money between 0 and 1. And so I get this vector, and my loss is just the inner product between d1, my distribution, and the loss vector. All right. And so now presumably I want to kind of shift some of my investment to the experts who are doing well. Right? And one good way to do this is to use the multiplicative weights update rule due to Littlestone and Warmuth, although it's been sort of rediscovered in too many contexts to count. And don't worry so much about what it is. The point is basically it's just a way of shifting towards the experts who lost the least money, or towards the experts who away from the experts who lost the most. So now, I have a new way of investing my dollar, and we get some losses on day 2. And that's how much money I lost. And I'll just say, the losses on day 2 can be chosen kind of after seeing what's happened on day 1. All right, sort of an important property, although I'm not going to say too much about it during the talk. All right, we go through this for t days. And what do I want to guarantee kind of at the end of t days? Like, it's a natural thing that I might want to say. I can tell you're like the only person who's going to answer my questions.
That you're not losing more money than the single fixed best expert in hindsight.
Right, beautiful. So, right, I'm going to look, really silly if at the end of, at the end of the year, I could have just, put my money with one person, and that guy did really well, but I put my money with, a bunch of clowns. So, what I want is a guarantee like this. And in fact, the multiplicative weights update will give me this guarantee. So first, ignore distribution for a second. What it basically says is, no matter what the losses are, if I look in hindsight and I pick any single expert, the amount of money I lost, that's kind of this sum of dt.lt, minus the amount of money that expert lost, which is the sum of d.lt, is going to be bounded. And what's a good bound? The most that expert could have lost was t. So I'm going to get a bound of root t. So I'll have lost something that's kind of sublinear in the number of days. And in exchange for this, I'll pay this factor that's logarithmic in the number of experts. All right. So this is kind of the magic of multiplicative weights, is it only gets this logarithmic dependence on the number of experts. I should say there's a constant in there, but I'm sort of allergic to having extra constants in talks. So, all right. So guarantee clear. This is a very useful property for things way beyond differential privacy. So if people haven't seen this, this is like a really cool thing to know.
And it can't be improved upon.
Yeah. So this is like tight in general. Okay. So yeah, this is the sort of optimal algorithm for this level of generality. All right. So it takes a little work to see what this has to do with answering counting queries. But let me transform the problem a little bit. So the way I defined it, I have this database that's a collection of n rows. And I ask a question that's what fraction of those rows satisfy some property of interest. I could also view my database as a distribution on the set of possible rows. All right, so database and a distribution are sort of the same thing. And so now I'm going to write my database as this huge vector saying what fraction of people are of each type. And in this representation, the query can be written just as a vector that says which types of people satisfy the property. And so sometimes people call these linear queries because of this representation that I can write Q of D as just the dot product between D and Q. All right, so this is just like a transformation of the problem into this really high dimensional space where the queries are now linear. So once you have that, you can actually do just like a pretty kind of syntactic translation. So I'm going to think of this no-regret learning algorithm now as an algorithm that's trying to learn the database. All right, so instead of thinking of my set of experts as just experts, I'm going to think of them as possible rows in the database. This algorithm is keeping track of a distribution over those possible rows, so it's really keeping track of a database in this high-dimensional representation. And now what it's doing is it's basically continually adjusting the database in response to the losses it sees. And I'm going to think of the losses as the truth table of the query. So for every expert x, every expert little x, the corresponding loss is going to be 1 if that person satisfies the property. Right? And now just purely syntactically, this is the guarantee I get. Yeah?
Did you rickroll us on the last slide?
I did rickroll you at several points. Thank you for catching that. Not enough people ask questions explicitly about whether they were rickrolled during my talk. Right, a minute to get back into the talk mode. Okay, so purely syntactically, this is what the no regret guarantee becomes. All right, so the set of experts has size 2 to the d, so that becomes d. And let's look at what this says. All right, I'm maintaining kind of an iteratively changing approximation to the database, d1 through d capital T. And, well, this is the regret I have. It's the amount, it's the sum over all the days t of the amount by which my current approximation overestimated the answer to the query. All right, so we have a bound over all t steps of the total amount by which I overestimated the answer to the query. And it's a bound that's kind of growing sublinearly in t. All right, so this kind of suggests the following thing to do. I put in purple the places where we had to make kind of a design choice. So let's use multiplicative weights as that design choice. Let's start with the uniform distribution. And let's find the worst query. And every day, we're going to do the multiplicative weights update with that query. All right, so this is still a non-private algorithm. But I claim this is going to have some good properties that are going to make it easy to make private. All right, so remember I said that the goal would be for this algorithm to kind of converge to the real database fairly quickly. All right, that's what I said we kind of need for privacy. And let's look at sort of why that might be true. So this is the regret bound I have. I said that for every kind of sequence of queries you choose, which correspond to losses, the sum of the amount by which I overestimate the answers to the queries is going to be bounded. So let's suppose that every day I manage to find some query for which my current guess overestimates the answer by alpha. All right, then I can take my regret bound, and on the right, I can say that, well, the total amount I overestimate is at least alpha times t. All right. So now just rearranging, what I see is that kind of the longest sequence of queries I find that can satisfy this property is going to have length about d over alpha squared. And since that's the longest sequence I can find, if I have managed to actually do this for t steps, at the end of those t steps, I actually must have it be that there's no query. In fact, not just in my query set, just there's no query for which I overestimate the answer by more than alpha. Right? And now, this is a good point to say I've been kind of cheating a little bit. So I keep talking about overestimating the answers to queries. This is just a simplification, but it's OK because I'm just going to assume the set of queries is kind of closed under negation. So if there's a query for which I underestimate, there'll be some query for which I overestimate. So this is really the statement I want, right? This statement is exactly the definition of saying that dt is kind of an alpha accurate answer to the family of queries Q. Picked a good time to pause, apparently. All right, so let's go back to the picture of what the algorithm is. And now I get to say exactly how many rounds I need to run this algorithm for. All right, so I only need to run this algorithm for about d over alpha squared rounds.
John,
Yeah?
can you go back, please?
Absolutely.
So you emphasized that not only, you said, was there no query in Q for which you would have a difference that exceeded alpha,
Right.
but that there is no query at all.
Right. I mean, if I can actually, do this. I mean, if I really find like a maximal sequence of queries that satisfy this property, then yeah. So obviously, I won't be able to answer, every possible query and still get privacy. But in principle, if I made Q be like all the queries, I could eventually run this algorithm and just, learn the, the whole database exactly in the non-private setting. Okay. All right. So back to the blueprint. We've up to privacy. This is sort of the whole algorithm, right? So this is just an algorithm for learning the database. And so far it doesn't do anything for privacy, but I claim it's a good one to make private. So just again, the algorithm is, you start with the uniform distribution, viewing the database in this big high-dimensional representation. You run for about d over alpha squared rounds. Every round you choose kind of the worst query. And then you run a multiplicative weights update. At the end of the day, you output the last database. And notice that this is a fairly small number of rounds to run for. Right? The set of queries, I think typically you should think of as much larger than this quantity. Right? So for instance, if alpha is a constant, this is like saying you can only ask like a constant number of queries about each attribute. And so typically this is going to be a small number of rounds compared to the trivial solution where you just ask all the queries. And what do we have to do to make this a private algorithm? Right? So we only touch the database in one place. Right? I put it in red to indicate this is where we touch the database, so it's the only thing we actually have to worry about possibly not satisfying differential privacy. Yes. So we have to make it differentially private. And I claim there's a really good way to do that. So it's something that Katrina went over in her talk yesterday. Let me just give you kind of the skeleton of what the tool is. It's a really useful tool to know for differential privacy. So it's called the exponential mechanism. It's due to McSherry and Talwar from 2007. And what it does basically, what's the problem I have? I want to choose from kind of a discrete set And I want to choose an element from a discrete set that maximizes some quantity that depends on the data. But it depends on the data in only sort of a mild way. So changing one row of the database can't change this difference by too much, right? And so the idea is that I can't just choose the maximum. That could depend on the data. I can't just choose the argmax. But what I can do is I can sample a query in a way that puts most of the mass on queries that make this quantity large. And there's a particular form for how you want to do that. You choose some privacy parameter epsilon 0, and you sort of exponentially weight towards queries with large answers. All right, so how you actually set this up is sort of not what I want to talk about. The point is that there is a way of making a distribution that's differentially private and shifts a lot of mass towards good queries. And here's the kind of guarantee it gives you. So kind of ignore this first part. What it's going to do is it's going to output some query q sub t, whose score, right, so for which this quantity is at least the max minus some error, alpha over 2. All right, that's the type of guarantee it gives me. It gives me something whose score is close to the best score. And in order to do this, I need enough data to make this distribution kind of concentrated on good queries. And it turns out the amount of data I need is about logarithmic in the number of queries and inverse in the alpha, the accuracy parameter alpha and the privacy parameter. And so the key here is this logarithmic dependence on the number of queries. That's what makes the exponential mechanism really powerful. You get to choose from a huge set, but you need data that depends only logarithmically on the size of the set. If you just naively kind of estimated all these quantities by adding noise, you would need something that depends polynomially on the number of queries. All right, so this is the tool I'm going to use in the multiplicative weights algorithm. All right, so now in order to get a private implementation, instead of choosing the argmax, I'm going to sample queries in this way. I want to just call out like a quick connection to another quick connection to learning. So if you look at what I'm doing here, I'm actually solving an agnostic learning problem. So I am trying to find a hyperplane, Q, that sort of best classifies data elements as being either from this fake distribution dt or the real one d. And I'm trying to do it privately. So really kind of any private agnostic learning algorithm will do here. That's sort of a useful perspective to keep in mind for variance. This is just a generic private agnostic learner from a paper by Kasiviswanasan et al. From 2007. That's all it is. All right, so this is almost the entire algorithm, except for one more thing, which is what privacy parameter do I use here? I left it at just some sort of abstract epsilon 0. Yeah. Yeah, so sorry, it's a little bit, so I mean, you can make it formal, but the way I said it was a little half-baked. The idea is that basically this quantity, this inner product of dt minus d and q, is basically sort of how well q, the vector, kind of separates points as being either from dt or being from d. Right? So these are both kind of collections of points. And I want, this will be large if kind of, more of the points in dt fall on one side of q than the points in d. So that's exactly like an agnostic learning problem. It's finding the hyperplane that best classifies your points. Does that make any more sense than the first thing I said?
What's agnostic about it?
So there is no perfect separator, right? So it's not the case that like every point in dt satisfies the query and every point in d doesn't. It's just, points in dt are slightly more likely to satisfy the query. Okay, so this is the algorithm. And as I said, the only condition I need basically is that as long as there's some query with error, let's say alpha, I need to find a query with error, let's say alpha over 2. Right? I mean, that's the condition. I need to make sure that I find a query that's sort of good enough to make progress as long as one exists. And I told you that basically in order to guarantee that I do that, I need enough data that this algorithm works well, and that amount of data is this quantity. And how many times do I need to run it? Well, I need to run it t times. So let's just remind ourselves what the composition theorem says. This is the kind of strengthened composition theorem due to Dwork, Rothblum, and Vedon. And what it basically says is that if I'm shooting for epsilon delta differential privacy, and I want to get it by running t separate algorithms, possibly adaptively chosen, then I need to run each one of those algorithms with some parameter epsilon 0 that's approximately epsilon over the square root of t. All right, and there's some fudge factor delta in here that will pop up here. But basically think of it as I want epsilon differential privacy, so I need to use epsilon over root t differential privacy at each step. All right, we have a nice bound on t. You can just plug it all in. And this is the algorithm. And notice there's only one place where I needed to assume I had a lot of data, is to make this step work. And here's how much data I need. So I'll unpack this on kind of the next slide. All right, this is the summary. So this is what we get. So we have this algorithm. It takes in a database and a set of counting queries you give it. It satisfies epsilon delta differential privacy. And it's going to, at the end of the day, output some database d sub t, such that if you evaluate any of the queries you asked on that database, you'll get a very similar answer to what you would have gotten on the real database. And the amount of data you need, it's only growing logarithmically in the number of queries. It has this kind of dependence on the number of attributes in the database. And it has an inverse polynomial dependence on the accuracy parameter alpha, and this kind of linear inverse dependence on epsilon. And some delta and some failure probabilities that I'm hiding. All right, any question with the algorithm, what the guarantee means?
Can we do this non-adaptively? Is there a separation between the guarantees we get here and if we did it, sort of try to do things non-adaptively, meaning not in an online fashion?
Right, so you mean you just want to sort of like find a fixed set of queries?
Yeah, or I just hand you some big bucket, some big bucket of random queries and say, if you answer all of these relatively accurately, I can find a database that's going to have small L1 distance from the true database.
All right, so there's a couple things. So finding a database with small L1 distance from the true database sort of is a privacy violation. I mean, that would be.
Sure, yeah.
But the question is, can you find a database that sort of, looks like the real one with respect to these queries? And the answer to your question is sort of yes. So if you take, say, this big set of queries Q and you just choose a random set of about n of them, and now you just find a database that answers those queries well, then generalization will apply. It will actually do well on average for the queries in Q. I don't have like a completely convincing answer off the top of my head. I would guess somehow, at least in this framework, if you want to answer every query in Q, you kind of need the ability to answer some accurately, see which ones you failed on, and
There's no small set of queries that without seeing the database. There's no small set of queries that for every database implies the answers to all of the queries.
At least in general. In some specific cases, there are. Does that answer your question?
I mean, I think it would probably take a lot longer to answer sort of the legally fit of the question, but yeah, it's good enough now.
All right, well, thank you. All right, so this is what you get out of multiplicative weights. This is one algorithm in a huge space of algorithms you could have used to solve this problem. So I want to talk a little bit about why this is a good one. And I think one of the reasons to say this is a good one is because it's sort of nearly optimal at this level of generality. And so, this isn't a talk about lower bounds, but since, according to Katrina, I'm like the Grinch who stole differential privacy, I'm sort of obligated to give you a lower bound in every talk. You're going to get 2. So in recent joint work with Mark Bunn and Salil Vadan, what we showed is that basically, for this kind of guarantee, multiplicative weights is optimal. So if you want an algorithm that takes in a large set of queries, an arbitrary large set of queries, it needs to have this much data to work with if it's going to satisfy accuracy and privacy. All right. So I don't want to overstate this. This is for some set of queries. Yeah?
The previous one was what's specific about counting queries in this result?
In which result? Oh, okay. So notice, I needed to be able to to make this algorithm work, I needed to be able to express my query as kind of an inner product between some representation of the database. If you have queries that aren't counting queries, that aren't sort of like linear in the set of rows, you can always do this by kind of blowing up into like an even higher dimension. You'll get a kind of similar type of guarantee. And I'm not sure if you get bounds quite this strong, but basically this works for kind of any query whose sensitivity to changing one row of the database is 1 in n. Right? That's sort of, for privacy, that's the only property of counting queries I used. For this particular algorithm, I used a little bit of additional structure.
And alpha is how close the true answer.
Yeah, so think of alpha as like 1 in 1,000 or like 1 in root n or something. It's between 0 and 1.
Is there some dependence on delta?
Yeah. There's like a logarithmic dependence on delta. Square. Well, in this, in my preferred language, it's just a log. But yeah, there's some dependence on delta. Yeah, it's log 1 over delta.
And where does it come from?
No, because he's changed it to.
So it comes from. So notice, see, I said you need to run it with privacy parameter kind of epsilon over root t. Really, you kind of need to run it with privacy parameter like epsilon over root t log 1 over delta. I mean, yeah, so the composition is basically a concentration of measure statement. So it kind of says that, the expected privacy loss kind of grows as the square root of t. There's some probability that it will like massively exceed its expectation, and the log 1 over delta kind of controls that probability. But I hit it because there's, just too many parameters in some of these problems. Had to pick one to go.
So if we did this with epsilon 0, would we get epsilon squared then?
If you did it with epsilon 0, you would get like a d here and an alpha cubed. You would actually still get an epsilon.
Okay.
But yeah, I mean, when you get something worse. But that's a good point. So everything I'm saying is going to have sort of an epsilon 0 analog if that is something important.
Except for the thing you said about arbitrary low sensitivity queries.
That's right. Good point. Okay, everything I put in the slides. Okay, so all right, so this is one lower bound says, this is sort of the right algorithm for answering an arbitrary set of queries if what you care about is how much data you need. But, I did something like very wasteful in designing the algorithm. I took this nice compact database and I blew it up into this huge, 2 to the d dimensional vector. So you might think that that's, it is imposing a big cost. So basically, what is the running time of the algorithm? In most reasonable settings, it's going to be dominated by the need to do this multiplicative weights update step on like 2 to the d experts. And of course, it's got some other factors in it. So like, you also have to just be able to evaluate the query non-privately. That might itself be already inefficient, but typically won't be. So the real, the dominant factor in the running time is this 2 to the d, exponential in the dimensionality of the data. And even though it seemed like a very wasteful step in the algorithm, that's also actually inherent for kind of an algorithm at this level of generality. So if I want some differentially private algorithm that I can give it sort of an arbitrary set of queries, it kind of runs in sort of genuinely polynomial time in its input length, then it needs a lot more data. It needs like square root of the number of queries, records in the database, which is what I would have needed for this kind of trivial approach of just adding noise independently. All right, and this, for people who, these things, this is sort of under the assumption that we have secure crypto, which is a fairly believable assumption, I hope. All right, so I don't want to overstate this either. Actually, Katrina and Frank and Moritz have sort of an implementation of this algorithm where they show it can be practical in some cases when d is not too big. There was a talk by Justin yesterday about kind of a variant of this algorithm that can be even more practical in some settings. But at least in theory, this seemingly very wasteful step is actually kind of inherent for any approach to solving the problem. All right, so this algorithm basically gives kind of the optimal amount of, the optimal data requirement and the optimal running time for this problem. So it's a very strong problem, but this is sort of, in some sense, the right solution to it. All right, so that's sort of all I have to say about what I call offline multiplicative weights. This is kind of the thing I'm going to go into in like the most depth. For the rest of the talk, I want to I want to give a few variants. So first, I want to talk about a variant to the online setting where you don't actually have the set of queries up front. Then I want to talk about just variants to special cases of the problem. And then I want to spend a little time zooming in on kind of a particular special case of the problem where the queries have a very nice structure, which has been an open, and it's been sort of an open problem in the literature. And I want to talk about how different learning theoretic techniques, sort of in conjunction with multiplicative weights, give interesting solutions. All right, so what's the online problem? It's exactly the same, except instead of getting a big set of queries and producing some summary, I just get an online sequence of queries, and I just give out an answer to each one. So, and this is a good point to reflect. Notice that the algorithm we designed that I just talked about was based on online learning techniques, but it was solving an offline problem. The online learning was just useful for getting a nice algorithm that we could make private. But of course, it also kind of naturally leads to an online algorithm for the problem. And so, what's the challenge about adapting this to the online setting? Well, one step in the algorithm was to I have all my queries, and I just sort of ask, is my database good for all these queries? And I get back one of the queries for which it's not good. Right, in the online setting, I can't do that. I mean, I get this query, and I have to answer it. So all I can do is I can ask, is my current approximation good for that query? I mean, it's sort of, the only obvious thing to do. And maybe I find out that it is, because, it's not a very good approximation to the database in general, but for one query it might be fine. So maybe what I'll do is I don't want to give out anything dependent on the real database. I'll just give out the answer on my approximation. Intuitively, that's kind of a good way of not revealing too much about the real database. But it doesn't solve the problem because just this information that this is a good approximation reveals something about the database. All right, so the blueprint just kind of proceeds this way. Now I get some other query, and I ask, well, is my current database good for that query? And maybe this time it's not. Right? I find out it's not. Its answer needs to be different. So maybe in this case I'll bite the bullet and I'll give out a noisy version of the answer on the true database. Right? Or just, ignoring privacy for a second, I'll give out the answer on the true database, and we'll just sort of remember we have to worry about privacy here. But, at least someone was nice enough to ask a query that gives me some information about the database, so I'll run the update algorithm, and I'll try to refine my approximation. And I'll just kind of proceed this way, right? So instead of sort of only finding queries that induce updates, I'll go through this whole process, and at every step I'll classify the query into either one we already do well on or one that we need to do an update on. Okay? And from a privacy standpoint, the hope is that maybe these queries where I just say, you know what, the current approximation is all right, don't actually cost me much from a privacy standpoint. Maybe I only need to pay for these updates, and the advantage is that there won't be that many updates. So the same argument for why we only needed a few steps in the offline case will also apply to the online case to say that there can only be a small number of updates, even though there are lots of queries. All right, so this is kind of a pseudocode for the online framework. I just get the sequence of queries. Every round I check, is my current approximation good? If it's good, I answer with this kind of default answer. If it's bad, I'm going to answer with using the real database, but I'm going to do an update. And I claim that I won't do that many updates. But I still haven't explained why this is private. So in this case, this only happens a small number of times, so I can solve it by just adding noise to the answer. I don't want to go into exactly how much noise, but the point is that this only happens a small number of times. I just add noise, and it's a good approach. This sort of thing can happen a lot of times, and we need something to argue for why it doesn't hurt us. And arguing for why it doesn't hurt us too much is a little too technical for the talk, or just too many things. But I want to just explain a very nice primitive that I think for everyone who actually designs differentially private algorithms is really useful in theory and in practice. And I think it's good to know, and this is one application of it. So here's the primitive. I think it's called the threshold algorithm, or sometimes the sparse vector technique. And here's what it does. So suppose we have a stream of queries that are arriving online, and somehow someone has just promised us that there's only a single query whose answer is larger than maybe alpha over 2. All right? Forget why that might be true, but maybe I just know there's not a lot of queries whose answer is large. Then I claim there's an epsilon 0 differentially private algorithm that with high probability will give me an accurate answer to every single one of these k queries, as long as the amount of data I have is about logarithmic in the total number of queries. All right, so if I just answered each one of these queries with noise, I would replace this log k with a root k. But because I know that most of the queries have kind of dull answers, I can improve it to logarithmic in the number of queries. All right, this is just a really useful primitive. And it takes a few steps to see how it applies here. But intuitively, the queries are going to be how different is my approximation from the true answer to the query you asked me. All right, and if I sort of break this whole algorithm up into these kind of blocks, where I think about all the queries before the first update, all the queries before the second update, and so on, each one of these is going to be some stream of queries where only the last one had a large answer. And so I only need an amount of data that's kind of logarithmic in the length of the stream, which at most is the length of the whole stream. So that's where I'm going to get my kind of logarithmic dependence in the total number of queries, even though in principle I'm giving up a little bit of information, at every round. All right, so it's just a high-level overview of what's like the main idea in going from the offline algorithm to the online algorithm. I probably went by a little fast, but I think this is like just a really useful thing to be aware of, is that if you can sort of guess the answer to most of the queries, you only pay for the number of times your guesses are wrong. All right, and if you actually work this out formally, you get basically the same guarantee that we got in the offline setting. So we had this optimal algorithm for the offline setting, and it turns out you give up almost nothing to work in the online setting. So the running time guarantee changes a little bit in that now you talk about how much time it took per query. It's, in the worst case, I did an update. It was 2 to the d, but everything's basically the same. All right, so that was offline and online multiplicative weights. Let me just really quickly kind of summarize some variants of multiplicative weights that have also been used in the literature to solve special cases of this query release problem. So, these lower bounds tell you something about answering arbitrary queries. What about kind of interesting special cases? And the big point here is that by having this blueprint for an algorithm that separates privacy from this online learning component, I can just swap in a good no-regret algorithm, a good online learning algorithm, and solve new problems, potentially using some additional structure of that problem. So the first place that we did that is in joint work with Anupam and Aaron, where we were interested in answering queries on graphs. So basically a special case of counting queries where each row of the database is like an edge, and I want to know what fraction of these edges cross between some set S and some set T. The results themselves are not particularly, I don't want to go into. I just want to say that in some settings you can actually reduce the amount of data you need for this problem over what you get by applying multiplicative weights using a different algorithm based on the cut decomposition of Friese and Kannan, which I think is really just like gradient descent. But I like to call it the cut decomposition because it sounds specific to the problem, which is also why we thought to use it. All right, so kind of an even nicer example of this is something done by Jane and Thakurta, where they replaced multiplicative weights with algorithms from the mirror descent family. So like a very general family of online learners that includes multiplicative weights. They also had some applications to cut queries. The main idea here is that when you know something about kind of the norm of the database and the norm of the set of queries, you get to get a regret bound in terms of those quantities. So multiplicative weights, we kind of view the database as a distribution. It has small L1 norm. The query has small L infinity norm, and you can consider other norm pairs. And that gives you interesting things in certain special cases. There's also work by Blum and Roth on kind of sparse queries. So there they were more focused on the running time. So you want to run kind of an implicit version of multiplicative weights in the case where each query only accepts like a small number of things. Aaron doesn't even seem to like have heard of this result, which is amazing. He's like looking really skeptical.
We're trying to decode the pictures.
Oh, great. No, I'm really glad you asked. This is when I Googled for sparse. Like I tried Googling a bunch of things involving sparse, and I eventually got this picture of a very sparsely populated Yankee Stadium during batting practice. That's apparently if you Google for like sparse population or something.
Running time or something.
Oh, no. So actually, this, by the way, if you Google mirror descent, is like the most literal thing you would ever think of from mirror descent. It's like a plane landing and its wing is mirrored. Some guy tried to sell this for like $5,000.
And you bought it.
No, I stole it.
Yeah, what was the licensing fee?
You go to Google Images and you take a screenshot.
It's not being recorded or rebroadcast, is it?
Uh-oh. Yeah, no, I was just kidding, obviously.
Educational purposes.
Yeah, there we go. Fair use. Okay, so that's plenty to say about sparse queries. It's also in a result that by Huang and Roth, they considered kind of distance queries. It's another counting query where it's sort of in a continuous domain, but the idea is that everyone is a point in some space. I give you a query which is some other point in that space, and you want to know the average distance from people to that point. And they showed how to get an efficient algorithm using kind of a specialized no-regret algorithm for the problem. And it also fits in this framework. So all these things just kind of come, you can only think about online learning. You don't have to think about privacy, and you can get all these things. All right, so the last thing I want to talk about is I want to zoom in on kind of a particular special case of counting query release that's gotten a lot of attention. And I want to talk about how we're sort of starting to make progress on that using a technique of polynomial approximations, which is really prevalent in kind of pack agnostic learning. And I want to say why that's useful for the problem. All right, so this was the generic private counting query release problem. I had sort of an arbitrary property that I wanted the rows to satisfy. And I'm just going to assume that the property I want is that the row satisfies some monotone k-way disjunction. So just the OR of some number of bits. And the number of bits will be at most k. All right, k is a new parameter. Since I introduced a new parameter, I'm going to take one away, and we're just going to fix alpha to be 1 in 100 for the rest of the talk. And of course, the sanitizer doesn't really take any input anymore. I mean, it just knows it wants to solve disjunctions. Right, useful facts for small enough, for a fairly small choice of k, like constant or slowly growing in d, the number of queries is not so huge. It's about d to the k. And also, this monotone disjunction is not really important. It could be a conjunction, non-monotone. Sometimes people call these marginal queries because I'm kind of asking for the marginal distribution on a small number of attributes. It's also sometimes called the contingency table, which is really widely used in like official statistics. So this is a well-motivated problem. It's an important one to solve for differential privacy. Let me just give you a sense of what happens if I apply generic techniques to the problem. So as I said, you should always think about what happens if I just write down the answer to all the conjunctions and I add noise, often called the Laplace mechanism. So the amount of data I need, square root of the number of queries, it's about d to the k over 2. The running time I need is sort of just proportional to the number of queries. That's like d to the k. On the other end of the spectrum, I could apply private multiplicative weights. I would pay this 2 to the d running time, which now seems fairly prohibitive because it's much larger than the number of queries usually. And the amount of data I need, if you just translate the bound, it's going to be about k, the number of attributes, times root of the dimension. And that's optimal for the problem. And kind of the lower bounds sort of say that there's like a threshold here. So anything kind of below here has to use some special structure of disjunctions. And this is maybe a bit strong, but I'll call it the holy grail of answering k-way disjunction queries. If you can get something that works with a database of size about k root d and runs in kind of polynomial time, like in k and d. All right. And as I said, like the bottleneck in this private multiplicative weights algorithm is sort of taking this database and kind of blowing it up to this huge distribution. And even though we know it's kind of maybe not it's specifically necessary, but this kind of running time is necessary, maybe we can do something more clever when we only care about a specific set of queries. And the idea is sort of just the following like switch in perspective. So normally you think of the queries as a function you apply to the database. I want to think of the database as sort of a function I apply to queries. So I want to think of the database as specifying some function f that takes the query and gives the answer. And so far this is sort of pointless, but the reason to do it is that sometimes when Q is a small set of queries or a nice set of queries, this will be a function with particular structure. So it'll be some nice thing. Maybe it will itself be like a half space or a disjunction or something nice. And we can get more efficient algorithms potentially by exploiting the structure. And that's kind of what learning theory does, right? So a lot of what learning theory is nice structural properties of simple functions like this. All right, so once you have this view, you can actually turn this into a general theory. So I only want to state an approximate theorem, but Hartroth, Ullman, Cervedio sort of basically showed something that has the flavor of saying, if this function is learnable, so if I can sort of, I don't know D, I know I have some function from this family, if I can learn it in a particular sense, then I get a query release algorithm for the family Q. All right, so this is sort of an approximate theorem. They do sort of a lot of steps and transformations and a lot of parameters. But this basically gives us confidence that when this function is learnable, we should be able to get an efficient algorithm. This, I should say, was sort of implicit in some earlier works on disjunctions. And they made it a nice general theory. But what I'm going to kind of finish up talking about is not the general reduction, but how to use sort of the techniques to get... Yeah?
What's CKKL?
Oh, Chiragshi, Clivens, Kothari, and Lee. The paper on... it has some title that doesn't include privacy. It's like the noise sensitivity of submodular functions, and it includes like a sweet result about privately releasing disjunctions as like a corollary somewhere.
So the class is a little bit different. It reduces to learning thresholds.
Yeah, so I'm really sort of deliberately, because I don't really want to talk about any algorithms you get out of this theorem. I just want to sort of say that, like it's not sort of it's not just an intuition. There is sort of a way of formalizing a connection. All right, but so I'm going to talk about sort of what some of the specific techniques are. I'm roughly going to sort of give something based on some joint work I did with Justin Thaler and Salil Vadan, and a follow-up with Karthik Chandrasekhar and Justin Thaler and Andrew Wan. All right, so just using this reduction that they gave, you basically get this result. You get that, you get roughly the same running time as the Laplace mechanism, at least polynomial. But you can improve the database size somewhat significantly when k is large. All right, so using this kind of connection to learning, I'll obviously say how the algorithms work. You can improve the data requirement. We showed in kind of a follow-up paper that you can also improve the running time. You can actually run in time sublinear in the number of queries, which is often hard to achieve. And then, what we considered in this follow-up work is what if I sort of take this database size as the hard constraint? So I really don't have that much data. I just want to do as much as I can for running time. And we gave some algorithm that runs in time sort of 2 to the little o of the number of attributes. Slightly. All right, so let me just sort of talk about the techniques that go into these results. I will say there are other results, some of which use learning theory techniques but give kind of average error variance. These are sort of nice, but I like to mostly focus on this worst case error. So I want accuracy for all queries. I also want to call attention to another result by Cynthia, Kunal, and Sasho that maybe one of them is going to talk about. I don't know. Where they sort of consider the opposite parameter regime, where running time is the hard constraint, and you want to get kind of an improvement in data, and they get sort of an optimal algorithm for k is 2. And this is using some sort of very different type of techniques, but it's worth keeping in mind.
Rump session.
Rump session. All right, there'll be a rumpus about this. All right, so finally, after sort of setting up the problem, I can sort of explain what the kind of main idea is. And, what did I say? I said we want to view this as a map that takes the description of a disjunction and outputs an answer. And I said that, because disjunctions are simple queries, this might have a simple structure. And what do I mean by simple structure? And roughly what I mean is that I can write, for any database, I can write this function fd as a linear combination of some small number of basis functions. All right? And in particular, I can write it as a linear combination where the sum of the coefficients is small. So that's what I mean by low weight. And this is sort of like the main kind of thing that underlies the most efficient distribution-free pack and agnostic learning algorithms. And I'll show why it's a useful concept. I'll also formalize what it means. Let's go back to multiplicative weights and see what it's doing. So I had a distribution over experts where there was one expert for every person that could be in the database. And the losses that I gave that expert were just whatever that expert would have said. So if I had a database that just consisted of that one person, how would that person have answered the query? And I want to think about this a little bit differently, using this sort of shift in perspective that I described. So what I want to think of the experts as functions. So there's a function for each record in the database. And the database is just kind of a linear combination of those functions. And because it's a distribution, its weight is 1. So the L1 norm of its coefficients, the sum of the absolute values, is just 1. And so I haven't actually changed what multiplicative weights is doing. I'm just reinterpreting it, where the experts are these functions f sub x, and the loss corresponding to each query, the loss for each expert for each query is whatever that expert would have said in response to that query. All right, so there's just sort of syntax at this point. All right, so I just want to think of multiplicative weights as sort of treating the database as like a weight 1 linear combination of some set of functions. And I'm going to think of this set of functions as the basis. And what happens if I change the weight? Right? So is the weight really all that important in multiplicative weights? I mean, I claim that it's not. So if I just, instead of distributing $1 every day, I distribute W dollars, I just, my loss is scaled by W and nothing happened, so my regret bound scales with the weight. Right? So this is sort of the important property I used for multiplicative weights was that oh god, I just used weight twice in the same sentence to mean different things. For the update algorithm, the weight of the coefficients was 1, but I can use sort of any weight that I want. All right, so I claim that sort of the private multiplicative weights algorithm is just a particular instantiation of this framework where everything's a weight 1 linear combination of a huge set of functions. And the huge set of functions is the bottleneck in the running time, but this weight 1 is why you get kind of optimal data complexity. So all the improved algorithms for disjunction queries that I'm going to talk about are just going to be just sort of changing this basis. So instead of having one basis function for each possible person in the database, I'm just going to have some set of basis functions. And I want to claim that I can treat the database as like kind of a low weight combination of those basis functions. All right, so let me just sort of give a definition of what I mean about that. I don't want to parse it completely, but remember I said I'm viewing this database as this map. So let's have a set of maps. This is my basis f. And I'm going to claim that it's sort of a good approximate basis for my set of queries. If for every database there's a weight W linear combination of functions that kind of uniformly approximates the database with respect to all the queries. And I'll just fix this desired degree of approximation. It's going to get rolled into sort of the final error of the algorithm. All right, this is clear enough. Again, I just have a set of functions, and I view my database as some kind of linear combination of those functions where the linear combination has bounded coefficients. All right, so how does this affect the final guarantee I'm going to get? So let me just assume I can construct one of these low-weight bases. This was the guarantee we had before. And what we show, although I should say it's a fairly sort of, mostly just follows from sort of techniques and learning theory, that if instead you replace your basis with something of weight W, you're going to blow up the amount of data you need by W, but your running time is going to just be proportional to the number of basis functions. Yeah?
This is probably a detail, I haven't seen this before, but when you're defining the database as a linear combination of set of functions, and implicitly you probably want to take a reduced dimension so some of the functions will be tossed. And I'm a little bit confused about how you go mapping from functions back to a database so that so that you have validity on the queries that you didn't include.
Right. So, okay, good. So that's sort of. So what I'm not going to do is I'm not going to output a bona fide database. So in the private multiplicative weights algorithm before, what I output was like a distribution over sort of possible people in the database, which I could just view as a database itself. Here, what I'm going to give you is like a distribution over these functions. And sort of the key idea is that the set of functions I'm using is sort of, they're only even defined on these disjunction queries. They don't even make sense. It doesn't necessarily even make sense to talk about what they mean for other queries.
So if you want to reconstruct the database with queries that would assume you have some set of rules, like uniform weights or something.
Right. So there may be some way of like taking the answers to all these disjunctions and kind of associating. In fact, there is. I can always associate it with some database that would give approximately those answers. But the key idea for efficiency is that I'm avoiding this bottleneck that's inherent for answering arbitrary queries by coming up with a representation that sort of only even makes sense for answering this small set of queries. And I probably should have said that earlier, so thanks for asking that question. Yeah?
I guess specifically for disjunctions, conjunctions, and we know it can be hard to, given just approximate answers to the queries, to generate a compactly.
Yes, we do. So I'm only allowed to talk about 2 lower bounds in this talk. So. What Adam's alluding to is that not only does this sort of seem to avoid the bottleneck of multiplicative weights, there's actually a lower bound that says any algorithm that privately generates an actual database that preserves the answers to this conjunction queries also has to have running time that's exponential in the dimension. So this is sort of using this kind of changing the representation is sort of inherent for this type of guarantee.
Can you just go back to the definition of the basis for a moment?
Yeah. Did I get it wrong?
So these f's are required to be 0, 1 now?
Oh, sorry. So this is not really important.
So they can be.
Yeah. I think you can actually, I think it's sort of without loss of generality. But yeah, so there's nothing special about them being Boolean. All right, so this just says if you have a low weight basis, you get a different version of multiplicative weights that's going to have a different set of parameter trade-offs. Hopefully I get better running time. And hopefully I don't blow up the weight too much. All right, and where do these low weight bases come from? They come from a very powerful technique that's used everywhere in learning, which is approximating functions by polynomials, preferably low degree polynomials with bounded coefficients. This is sort of usually the most efficient way of packed or agnostic learning most of your favorite function classes in the kind of distribution-free setting. And it's been used for disjunctions. Let me just explain what the technique is. So let me skip ahead a little bit. So I said I have a map from queries to answers. So how do I represent the query? Well, for a disjunction, let me just represent the query by some vector y, which says, it's going to have d bits, and it's just going to say which literals I include in the disjunction. All right, so like for this one, the vector y would be 1, 1, 0, 0, because 1 and 2 are in, 3 and 4 are not. All right, and I claim it's sufficient to just approximate one-row databases, because the database itself is a linear combination of rows. If I approximate each one by a linear combination, things work out. So what I claim I want is I want that for every possible row of the database, I have some function, p sub x, that it's a polynomial of degree capital T, weight w, and for every y that corresponds to a k-way disjunction, it's going to be a good approximation to f sub x. And when I say every y that corresponds to a k-way disjunction, notice that since this is a k-way disjunction, it only has k literals, so there's only k non-zero coordinates of y, even though it's a d-dimensional vector. So this is a slightly non-standard version of sort of a canonical problem in approximation theory. And it turns out, just purely by coincidence, that when I view this as a function of y, it's also a disjunction. So basically, you take all the ones that are present in the row x, and you look at whether any of those are actually asked about in the query. It happens to be a disjunction, but it may not be a k-way disjunction. It may have all the literals. And just by some sort of simple transformations, it's sufficient to approximate just the single d-variate OR function, which is a well-studied problem if the answer is known, but I care about, only about approximating it on inputs with at most k non-zeros. All right, so, all right, this is just a statement that says, if I have such a polynomial approximation, I get a low-weight basis where the basis functions are all of the monomials of a particular degree. That's what a polynomial is. It's a linear combination of monomials. And what I care about is the sum of the coefficients in the polynomial and the degree. All right, so I'm sort of starting to run short on time, so I'm going to maybe skip a little of the detail. But let me just say the key idea for why I can get a non-trivial approximation to the OR function. And it's this picture. So let's just consider a univariate function. And I want it to be 0 when evaluated on 0, and I want it to be 1 when I evaluate it on anything from 1 up to k. Or, say k is like 20. So I want a function that kind of looks like this, except I want, these things to be like really close to 1. So just using polynomial interpolation, I can always get a polynomial of degree k that does this. But there's a really nice polynomial called the Chebyshev polynomial that approximately does this, and its degree is only about root of k. Yeah?
What is the y-axis?
And the y-axis is the value of the function. It's just a univariate function. All right, so let me kind of skip over this and just get to the punchline. Using just this univariate function, I can derive a polynomial that approximates the d-variate OR function on all the inputs with at most k non-zeros. Its degree is going to be some constant times root k. And its weight, the sum of the absolute values of all of its coefficients, is about d to the square root k. All right? And plugging that into this framework, I get exactly this result. It's actually a different algorithm, but you get this result. You get that the database size is dominated by the weight, which is about d to the root k. The running time is actually going to be dominated by the number of queries, because the set of basis functions is very small. So you get a much better running time than multiplicative weights. You get a much better database size than the Laplace mechanism. You get something kind of weird in between here. Let me also say, let me just skip ahead. So in the low, suppose you don't want to tolerate this high weight, you want to get a very low weight, then there's a way of kind of composing two different approximations that will give you something with very low weight independent of k, just like a fixed polynomial in D and a very small one at that. And its degree will be non-trivial. So its degree won't be D, which is the largest kind of interesting degree. It will be some, D to something smaller than 1. And we also show that this kind of thing is optimal. So this is like a new result from work with Karthik, Justin, and Andrew, where we showed how to get this very low weight polynomial that approximates OR with some kind of non-trivial degree. All right, sorry for kind of rushing through this. Doesn't have that much specific to do with privacy, and that's kind of the whole point. All right, so we use that to get this point on the trade-off. We get something where we pay just a tiny bit in the amount of data you need, and you get some improvement in the runtime. So this improvement will be something like d to the 1 minus a little bit. And as I quickly alluded to, so we're able to this leads to sort of an inherently interesting question that is now abstracted totally away from privacy, which is, what's the smallest, what are the right sort of weight basis size trade-offs for interesting functions that come up, in the course of designing differentially private algorithms? This is a question that's actually been sort of very well studied for like 100 years, but the particular requirements of at least this problem of k-way disjunctions seems to lead to some new questions that haven't been resolved. So we were able to show that basically this sort of very small improvement we get is actually the best you can do if you use a polynomial. So if you want to keep the weight fixed, you can't reduce the degree any more than we do. In the high weight setting, this sort of thing was known, that polynomials are sort of the best approximation. It's the best basis you can get, due to Sasha Scherstov. At least a general theorem. Maybe a particular was known earlier. I'll just call attention to that, if you don't assume polynomials, you just want to know the smallest, very low weight basis for approximating all the k-way disjunctions. It's a nice open question that would be useful to resolve. And I'm sure by considering other families of queries, you get lots of questions of this variant. So maybe you can improve this. And I think that I want to conclude on this thought that I want to sort of go back to the slide I put up at the beginning. So, what I've just been talking about are ways to get really good private algorithms by using learning algorithms. And it might seem like a very limiting thing to do, but for general private query release, it gives you sort of the optimal algorithm in terms of running time and the amount of data you need. And, as I said, it fits in this very general framework where you can plug in, different algorithms and get different things for special cases. But in those settings like disjunctions, it's not at all clear that this gives you the best algorithms. I mean, it gives you improvements, but it's not clear why this should give you the best algorithms. And the reason is that it seems like there's like a whole huge space of ways you might try to interact with the database that don't fit into this framework of learning where we almost throw the database out completely and kind of reconstruct it using very limited access. So there are just a few cases I know of where you can actually get better results not by going through this approach. One of them is this work with Justin and Salil, where what we showed is that basically you don't need to do any of this multiplicative weight stuff. You have the database, you write down the polynomial, and you perturb its coefficients. And this actually lets you run in time sublinear in the number of queries. And also, this very new result by Cynthia, Sasho, and Kunal, where just using sort of completely different techniques, I would imagine. I mean, they at least seem very completely different. You get interesting algorithms that can't be matched by any sort of learning theoretic technique. So I just think that it's really good to be aware of these sort of learning techniques because they seem to give powerful results and were very important for kind of showing the power of private algorithms. But I really want to sort of conclude by shedding some doubt as to whether this is really like always the right set of techniques. So maybe a down note to end on, but like I sort of want to say it's good to keep these in mind, but don't get like locked in on them. So let me just summarize. Basically, what I gave you was some sort of flexible, very modular framework for designing differentially private query release algorithms using learning theoretic techniques. And this sort of mostly captures like interesting special cases we know, mostly captures the interesting query release algorithms we know. And I think a really good thing to think about is sort of what's the limit of these techniques? What are like extra ways of strengthening the techniques? What are different techniques? What are ways of relaxing the problem? Do different techniques in learning give you stronger things? So hopefully by being aware of what people have done with this, you can start applying kind of new, going beyond what's already been done in or out of this framework. That's the end. Thanks. Yeah?
Yes. So I noticed that when you looked at the databases, so the alphabet size was 2, right? So because there were vectors, d-dimensional vectors,
Sure.
and the elements were 0 and 1.
Yes.
So if the alphabet size is not 2, but it's larger, then what is the kind of dependence on alphabet size?
So are you talking just sort of general query release? Or
Yeah.
Okay, so in general, I mean, I can always treat the alphabet as binary. And if my symbols were from some alphabet sigma, I'll replace it with like log sigma bits.
Okay, so log sigma.
So, but that, yeah, so in general, you pay sort of log of the alphabet size. If you're talking about particular families of queries, they may, look simple when viewed on symbols from a large alphabet, but less simple when viewed as bits. So you might, make the problem a lot, like it might not be there might not be a simple like trade-off.
I see.
Like if you wanted to do sort of conjunctions over a large alphabet, blowing it up to binary like might make the problem a lot harder. So then I don't know what to say. Yeah?
Do you have any better trade-off lower bounds for the disjunction case?
Better.
Well, you showed the 2 lower bounds. I know you're asking to show more than 2.
Oh, well, Adam already made me show a third. No, so I mean, so the lower bound that we were able to show, right? So if I want to get, a small weight, like fixed polynomial in D, this is like the best degree you can get.
But that's not a lower bound on the actual.
Size of the feature space? Yeah, so I don't know. I mean, I don't know any I don't know, Justin, you know any like non-trivial lower bound on the feature space size?
As soon as we have the weight constraint, no existing techniques in the breakdown.
Right. So I mean, there's sort of a lower bound that applies for like any weight, but I don't know like why. I don't know anything. I mean, it's a good question. Potentially, you can get like much better algorithms this way.
So, in Justin's talk, he was talking about how in a case where the histogram size, the possible data entries is large, but the number of queries you're considering is relatively small, you can push all the hardness into just an optimization problem. Is there if you're in a setting where maybe you have both being large, like you care about all marginals,
right?
And but you also have big database. Is there a hope to, through some other means, maybe push everything into? I mean, suppose that we imagine that we've got good heuristics for NP-hard problems, so if we can just push it into that sort of a thing, maybe we can. Do things. So,
right.
Is there any hope that both are large?
I mean, I don't have a very useful answer to the question. Of course, it's possible. It's sort of a recent thing that Justin and everyone figured out how to push one of them into a nice compact problem. But I mean, I don't have like any particular candidate for a good solution. But it's a good question. I mean, again, I just gave lower bounds that are for worst case problems. But what are some nice ways? What are like good heuristics for solving the problem? And in particular, you need kind of compact formulations of the problem. So it's a big question. It's a good one.
Solving a linear program with both like lots of variables and lots of constraints. So clear at least.
Right. So I can think of ways to write it as sort of like sampling problems over both of these large sets, which in principle can be done.
Sometimes like if you have like say you want to solve for approximate mini-max optimal strategy.
Yeah, exactly.
Big both ways. And I guess what you sort of need is kind of a good best response.
Yeah, exactly.
Both sides somehow.
Exactly. So you sort of need both. But in general, like best response dynamics, I don't converge. Right. In principle, yeah, it's maybe possible. You can definitely write them as like sampling the best row and sampling the best query, which is a compact problem, even though it's a hard one. Sorry, that got a little like isolated over here.
All right, thanks.
Thank you.
We convene at 11:30.